So this represents the final full unit of this course, which has notoriously been the hardest of all of them. However, since you have equilibrium in your back pocket, you have KSP, you have some rate law, thermodynamics, this is the culminating unit. There's a little piece of electrochemistry you have to review, but this is it. And by the way, this is called the hardest of all the Part 2 questions. However, it's handicapped by the sense that you've done so much work already up to this point. But before we can jump into the equilibrium problems, which I would love to do, we have to go over the requisite skills in this. What makes this harder is because we have an extra layer of skills that we have to have when we deal with equilibrium problems. So it all starts with the autoionization of water. So when we talk about, this is going to be acid-base equilibrium problems we're going to get to, but it all has to start with the autoionization of water. So if we start with water, H2O, by itself, it's a liquid. By itself, it will self-ionize into what we call a proton. That's a hydrogen atom missing an electron, which has left a proton.
I feel like we haven't talked about protons in so long.
Oh yeah, we're bringing it back. And into the hydroxide. Squid is out of control today.
Yes.
Okay, now, as we go, now, there's another way to write this autoionization energy. I can write H2O, two of them, so I will, H2O, plus another H2O, and both of these are liquids, and these, of course, are ions in solution, aqueous. And you notice I'm drawing a double arrow to reflect that this is equilibrium. Now, in this case, the case that I've just drawn underneath, what happens is one of these waters gives another water a proton. And the one that accepts the proton is going to be called the hydronium ion, H3O+. Okay? And that sounds a lot like this one right here, which is called the hydroxide ion. Okay? So the hydronium, you'll hear that a lot. That's a water holding on to a proton. Now, the one that donated the proton now becomes the hydroxide. So both of these are equivalents of each other, or equivalents. So when we have water by itself, and guess what? All of our solutions that we deal with in organic chemistry essentially have water, so we're constantly dealing with this equilibrium. That's why acid and base is very important, especially in biological systems where enzymes, the soldiers of our biological homeostasis that run reactions through catalysts and enzymes, are dependent upon this ratio to be at a certain amount. That's what our pH is about. So this is really, really important in biological organic reactions. And since 99% of all reactions are organic, we have to consider this reaction or this autoionization all the time. So what am I after here? Well, one thing I am after is the fact that these two, whether it's a proton or a water holding on to a proton called a hydronium ion, these guys are due to, or we measure this in terms of acidity. They are synonymous. So we say that acidity, or an acidic solution, is a scenario where you have a lot more of these guys, either the proton or the hydronium. They're one in the same. So if they mention H3O plus or H plus, they are synonymous. Whereas the hydroxide, okay, that OH minus contributes to the basicity of a solution. Okay, so this one right here, hydroxides are the basicity of solutions. And their relative amounts compared to each other, okay, will do what? Determine whether reactions go or not. Okay, so it's very important in terms of biology, okay, about aqueous solutions. Okay, now, we said these protons and these hydroniums are synonymous. So from this point on, you're going to watch me write the H plus and a backslash or a front slash, I want to call it. I never knew the difference. What do we call that?
I think that's a backslash.
Okay,
It's
backslash.
called a slash.
Okay, let's do slash.
Backslash.
H3O plus.
A hashling slasher.
Whatever. So when I draw this, I mean the same thing. It's one or the other. Now, well, if we have a reaction at equilibrium, my friends in chemistry can't get away from it. What we have is we have a K value. The equilibrium constant, or the KEQ for this reaction, is equal to what? Products over reactants. Coefficients become exponents. Solids and liquids do not apply. So these are all liquids, or we say liquid, okay? And of course the ions are all aqueous. So my friends in chemistry, we're not going to eliminate a reactant here. Never. In KSP we do, because what? One of the reactants or the reactant was a solid. So I do products. Let's do the top reaction, but I'm going to combine these two. Okay, this could be H plus. Okay, or that slash we'll call H3O plus. And it's to what? A bracket to show to what power? What's the coefficient? 1. And we don't have to write it there. And then we have what else? The hydroxide, OH minus, to the same power. Now, what's so important about this? Let me rewrite this over here to make it bigger and use more of the board. Now, we'll just keep it where it is. Okay. Now, what's so important about this? Because this is such an important reaction to reactions in aqueous solutions, especially biological, we're going to rename this. For salt, it's KSP. For water, we call it KW. Okay, so KW is equal to that. Now, so that value there. And we'll just rewrite it because I'm being told. H plus slash H3O plus. These are synonymous. Either one of these can be rewritten here or written in this position. And then we have the hydroxide. Now, what do we know? Well, guess what? KW, like all equilibrium constants, are temperature sensitive. So we keep this at a temperature that we know of. We know the value of KW. And the value of KW, if you forget, is 1 times 10 to negative 14. No units in an equilibrium constant. So that's our equilibrium. KW is equal to that. Now let's think about this for a second. What is, and this is good stuff here, what is the stoichiometric coefficient? Now wait a minute, Mr. Grodsky, you wrote me an equilibrium expression that was on our KSP quiz yesterday. It looks a little different, but wait a minute, why aren't there any reactants? What doesn't apply? Because they have no molarity. Only what? Aqueous or gases have a molarity. So that's why you don't see that. But what's the coefficient? For every one water, how many H pluses and OHs do you see? 1. So it's a 1 to 1 to 1. If I do an ice table, this would be pure water would be what? Plus X, correct?
Correct.
So wait a minute. If I know that KAQ is 1 times 10 negative 14, this would be an X, and this would be an X. And what's the square root of 1 times 10 negative 14? 1 times 10 negative 7. Oh my gosh! If these have to be equal, doesn't it make sense that those X's, or those values in those concentration, have to be 1 times 10 to the negative 7? Watch if you don't get it. 1 times 10 to the negative 7 times another number, which is the hydroxide concentration. Don't forget, these are molarities. Equal this value, 10 to the negative 14. Doesn't that make sense? Yes. If I have pure, unadulterated water, nothing is in the water but just pure water, I have to have the same amount because 1 H plus, or 1 water breaks apart into 1 H plus and 1 hydroxide. These have to be the same. Therefore, what number times itself equals this number? Because we're dealing with exponents in very, very small amounts, we add the what? Coefficients. That's imperative you understand that. Now, what's that? Okay, so let's continue. Let's pretend I'm a princess, and let's pretend I increase the concentration of, well, the acid which reflects that I'm going to have more protons or hydroniums than hydroxide. So now I'm in a solution where there is more H pluses than hydroxides. I have an acid that has adulterated my water. Okay? I'm not sure what that means, but okay? I'm going to go with it. Okay? Unadulterated water, pristine water, it'd be even. But now I've got an acid in there adding to and contributing to the protons or hydroniums already in there. So I'm going to increase this number 1,000 times. Yes. And this concentration of H plus now is 1 times 10 to the negative
4.
4. 1,000 is 10 is what?
To 3.
To the negative 3. So I increase this 1,000 times. Okay, party people? What must happen to the hydroxide ion concentration? It's got to go down 1,000 times because Kw doesn't change. So if this is going down, the other one's going to go up to balance it off. We learned about that. If you do what to Q, what happens? K is going to stay constant, right? So this is going to adjust itself to reestablish at a new, at the same Q but a new value. So 4 plus what is 14? Okay, what? Yes, this becomes 1 times 10 to the negative 10. And we all should see that that number got smaller.
Yes.
And what do we know here? Okay, we know when the pH, we know when the H plus or the H3O plus is greater than the hydroxide. We call this what range? The acidic range. Now, my friends in chemistry, we're never going to be dealing with these small, tiny little numbers of OH and H plus in water. It's really, really cumbersome. So what we're going to do is going to use a system, base 10 logs, to help us take such a tiny number and make it into just one number, the exponent. See, scientific notation, what this is in, takes a small number and makes it manageable. This is really 0.0001. This is really 0.9 zeros and a 1. So this is making it more reasonable. We're going to make it better. We're going to put the entire number into an exponent. And that's what pH is, if you remember. So pH is called the negative log. So here's what I do with this. I'm going to do the negative log of the H plus ion concentration, or synonymous H3O plus concentration. So that's what I'm doing here, the negative log of that. Now, what does negative log mean? It means find the exponent of this and times it by negative 1. What's the exponent of 1 times 10 negative 4? It's negative 4. Times it by negative 1. 4. This is a pH of what?
4.
pH of 4. So you take the negative log, you get a pH equal to 4. So negative log means what? It means stuff that number into an exponent. So if you have your calculator, you're not going to deal with these numbers. This could be 2.3 times 10 to the negative 6. I will take log button of 2.6, I'm thinking of whatever it might be I just said, find that value, times it, change the sign, times it by negative 1, and that'll be my pH. What is it? I'm stuffing the entire concentration into an exponent. And I'm putting a negative in front because we want to live in positive values. Now, don't fall in love with pH. Because sometimes you have something called a POH. What is that? That's the negative log of the hydroxide concentration. Now, these are easy numbers. What's the exponent of 10 to the negative 10? Negative 10 times by a negative 1. So this is going to be not the pH, the POH. So if I'm looking for the pH, or guess what? Can you imagine an equilibrium problem where they give you the pH? Aren't they really giving you the concentration of the H plus ion? Yeah. So they're going to start you that way. That's so if they give you the POH, you can get the concentration of the hydroxide. But how do we go back? Well, we go negative log this way. To go back, we go backwards. Sometimes they call this the anti-log. You go 10 to the negative x. So you go 10, So right where the log key is, you got 10 to the negative x going back. So if I gave you a pH of 4, okay? If I gave you a pH of 4, you would do 10 to the negative 4 to get that back. Obviously, 10 to the negative 4 is 1 times 10 to the negative 4. So to go back, it's 10 to the negative x. And that's how you do what? Take the exponent and bring it back to the number. This is what we need for equilibrium problems. Acid and base concentrations live in these values. So 10 to the negative x to go back, negative log of this. The numbers are not going to be nice. So if I have my handy dandy calculator, let's do a couple, okay? At some point I'll find it. All right, here we go. So let's do some real life ones, because this is just silly examples where you'll never see it. On the Regents, we did it quite like that, okay?
Wait, why is it 10 to the negative x? I thought it was just like 10.
All because you did negative log going down. You took the exponent and made it, times it by -1 to make it positive. I got to bring back the negative value of the exponent because it's a small number. Okay? So here we go. So let's just say I have a pH equal to, well, let's do it this way. Let's say we have an H+ ion concentration first. Let's say the H+ ion concentration, which is equal to the hydronium, is equal to 2.6 times 10 to the negative 4. And by the way, this is a molarity. In the brackets, don't lose sight of that. Okay? And so all you would do is, very simply, is I would go hit my log key, log of 2.6. Now I'm a big fan of using the EE key, not the caret key. If you use the caret key, you have to use parentheses, and a lot of times you forget that. It doesn't lock the exponential with the value. So I do 2.6, second function, using the TI-84 plus West Hampton edition, but of course, okay? 2.6, and we're going to go EE key, and I'll go -4. EE key is going to be right under, okay? Okay, there's our EE key right there. So there's,
It's undersigned.
so we go right here, undersigned. So do second function. So for those that want to follow me, okay, on Twitter, no, just kidding. All right, so this is what I do.
My name is Big Z.
So I'm going to do this. I'm going to take 2.6. So I'm going to do the log of 2.6. I'll put the 6 there. I'm going to second function it. So I hit the second button. I'm going to do the EE key. Now that E, for those that can see it, this E flashing means 2.6 times 10. That E is the exponent 10. So you don't see the 10. So 2.6, then you have times 10, which is not there. That E means exponent of that times 10. And we're going to use -4 since that's my example. So I put -4 there. And I'm going to close the parentheses because I was doing a log of that. Okay, so 4, it probably doesn't have to. And so what I get is -3.58. But it's a negative log. Little p means negative log. So times that by -1, and what do you get? Right, so this gives me 3 point, let's do 1 to 3 point, so pH is 3.6. You with me?
Yes.
Very simple. Now, what if I want to go back? What if I was giving you the pH and want to go back? So what I do is clear my calculator, okay, and I would do, right here is 10 to the x key, so right where you had log, okay, you have 10 to the x, so second function, that's going to give you 10 to the x, we're going to do what? 10 to the negative x. So I hit a negative, Christmas in July, second function, 10 to the x, so I see a little 10 blinking, I go negative what? 3.6. Close my, and then I hit enter. And what do I get?
2.5.
Yeah, now the reason why it's not coming out exactly is what we did what? We rounded off some of that data, but we got backwards. So that's a requisite skill. You need to be able to go from the concentration to the pH and back. Okay? You're not going to be given those equal nice little numbers, except in the multiple choice, you'll be giving these values. Why? You're not going to have a calculator in the multiple choice. So you're going to be given these kind of values in the multiple choice. So you just go with the values. Now, what's so powerful with this is that now, yes?
Why don't they let you use the calculator?
Because they don't want you to bring a programmable calculator that you could program. For those that don't know, you could program all kinds of stuff that you want. You could write into your program, you can bring in periodic tables. There's all kinds of data you could bring into the test. They just want to control for that. You don't have time in part 2. They don't care, okay? But in part 1, they figure for 60 questions in an hour and a half, they don't want you pulling information from the other parts of the calculator to help you with any question. They make the math simplified enough that you're just dealing with concepts. You could, if you didn't know, you can program your calculator for any English or social studies dates you wanted to, and they don't want to do that. I know you could what? Clear them, but some don't clear the same way. They just take it off the shelf and say, you know what? We'll make the math easier. Don't bring it in. I want to see if you know the concepts. Okay, now.
Do we use these calculators?
Yes, use your own. They don't care what kind of calculator. Now, why is this important? Well, my friends in chemistry, let's continue on. Now, when the pH was 4, we had a pH that's less than what? 7. So when the pH is 7, think with me, party people, when a pH equals 7, this has to be 10 to negative 7, and this must be what? So a neutral pH, your H pluses or hydroniums equal the hydroxides. If this becomes a real small number, like 1 times 10 to the negative 10, what must this number be? Negative 4. So the pH becomes what if this is 1 times 10 to the negative 10? What's the positive value of the exponent of 10, right?
Yeah.
So when the pH is bigger, that means this number is smaller. That means the hydroxides are greater than that. So you need to know when the pH is greater, we say it's a basic range. So anything above pH of 7 is a basic range. And what does that mean? The hydroxide value will be bigger than the H plus or the H3O plus. And at pH, as we can see, the H plus or the hydronium will equal the hydroxide. That's almost never, ever, ever going to happen. Okay, it's almost impossible to try to get that. Even pure water is going to have some stuff mixed in. So now, let's talk about this. Next skill. If I've got a pH of 3.6, here's a great question. What must be the hydroxide concentration? Okay? Now I'm going to take this away. So I want to know. I just figured out, remember, Kw is equal to what? Let's keep it as H plus or H3O plus, I guess I'll write it anyway. Times the what? Hydroxide, that's the equilibrium expression. So if the pH is 3.6, I want to know what the concentration of this is. Well, we have a nice little thing here. Next skill, very important. Okay? What do we know, party people? Isn't this really exponents?
Yes.
So if the pH is 4,
Exponent's negative 4.
and this is going to be 10, right? Because this has to multiply into Kw. What is the POH in this case? It's the negative log of the hydroxide. What's the POH in this case?
10.
It has to be 10. Wait a minute. 4 plus 10. These are exponents. What does that equal? 14. Now who's 14? Oh, that's Kw, isn't it? So if we do pKw, what does that mean? Take the negative log of Kw. If you don't know what I'm doing here, Kw is 10 to the negative 14, right?
Yes.
Okay. So if I, let's get rid of this. If I do the negative log, going down, we'll get rid of these arrows. Arrows up are 10 to the x. But if I go negative log of this, don't I get 14?
Yes.
So what do we know? The pKw is equal to the pH plus the POH. This is really helpful. Watch what I do here. These are exponents, right? So 10 plus 14, 10 plus 4 is 14. So these are exponents. So watch how helpful this is. If I give you a pH of 3.6 and want to know the hydroxide, I know I can do 10 to the negative x and do what? And get back this value, which goes here. I know I have this value, and I can mathematically, given these two values, solve for x. Or watch what I can do here. If the pH is 3.6, I know that it adds to the what? POH. What's that number if it has to always equal pKw? So how do I get POH? What's 3.6 minus 14 is what? 10.4. We just solved, with very simple math, what the POH. If the POH is equal to 10.4, how do I get the concentration back? When I go back from a log to the actual number, I do what? 10 to the negative x. So I go 10 to the negative 10.4, and I would be done. So I take my later of calc here, and I go, second function on top of the log gives me a 10 with a blinking dot, and I go negative 10.4, and booyah, my answer for the concentration of my hydroxide is 3.98 times 10 to the negative 11. Which makes sense, it'd be small, right? Because if my concentration of my hydroxide, if I multiply these two numbers together, shouldn't that give me 1 times 10 to the negative 14 or something close because we rounded? Absolutely. Can you see the power in this? So I know by using my pHs, I can find my POH, and I can work backwards to that concentration. I know that I could have just taken this value and divided by kW as well. But having all of those tools in front of you will make these problems. We're going to be dealing with equilibrium problems that have this extra layer of things here because it's what? Acid and base. Okay? And that's what makes these equilibrium problems a little bit more challenging because you have these other factors that you don't have. So those are the requisite skills, okay, in the beginning. Now we have a little more to do, and I'll get to it. All right? Now, that's with water, okay? Now, so understanding what the pH is, if it's above 7, that means this factor, there's a greater amount. And the pH value will be higher because this number has to be smaller. Needs a what? A bigger negative exponent to make this bigger, right? And when the acidity, or we have more H pluses or hydronium ions, it's a negative acidic environment, this number is now bigger, which is a smaller negative exponent, which is going to give you a smaller pH, and when they're equal. So that you should have from last year, but the skills going back and forth are absolutely imperative to have. Now, there's a couple of things I want to go into before I run out of time. And that is, of course, the strength of acids and bases. Okay? So I don't know what I just did with it, probably right here. Okay, so the strength of acids and bases. Now, what does it mean to be a strong acid?
You're very low.
What is a Ka? This is now going to be an equilibrium constant for the dissociation of an acid into its ions. How come I don't have numbers here? K is equal to what? Products over reactants, coefficients become exponents, solids and liquids do not apply. If this thing completely dissociates, all your reactants are approaching 0. Isn't that a denominator? Your number is approaching infinity. So you can't really measure these very well. But what happens when your Ka becomes less than 1? Whose favorite? Products or reactants? Don't forget, K is equal to, just from our KSP, products over reactants. If your K is small, that means you don't have a lot of dissociation. Okay. I will post the homework. It's one of the 2 dittos. It's the ditto number 1 only. Okay? We're not done. We'll finish doing requisite skills tomorrow and then get into equilibrium problems.
Well,